Let's start. All right, so welcome to lecture 3. I started out by writing down some of the rules we looked at last time. I didn't quite finish. What is missing is tensor, but I also wrote down lolly, so tensor is the inverse. And then the other thing we looked at last was termination. Okay, I hope you otherwise have your notes. But anyway, we looked at it last time, but I just wanted to have it on the board so that you can just glance at it. So let's continue. So the program for today essentially is to continue with the Curry-Howard correspondence for linear logic, intuitionistic linear logic, and the session-typed process calculi, basically. And then we also, so the plan is to do some programming. I would like to implement at least the queue, so that I basically set you up so that later on you can play with concurrency, not yourself. Then I want to discover Bang together, which then paves nicely the way to talk about sharing on Saturday, where we really basically regain the full expressiveness of the pi calculus, which we, right now in the linear setting, we don't have. Okay, so let me briefly remind you. So as I said, I wrote down some of the connectives already. Let me maybe also just write down the correspondence that we discovered so far. So we have for the Curry-Howard correspondence between intuitionistic linear logic and session-type concurrency. So we have the correspondence. So over here we have linear propositions, and over here we have session types. So we have A with B, we had A plus B, then we had a lolly B, a tensor B, and we also looked at 1. So these are the connectives we looked at so far. So let's briefly revisit what the interpretation was. How did we interpret with in a session-type setting? So what does it give? What does it provide in terms of session types? It's an external choice. Yeah, thank you. So it gives the client the option to choose between several options. In terms of the queue, it gave the client the choice between either enqueuing or dequeuing. So then what is plus? Right, that's the internal choice. So which gives is the inverse, it gives the provider the choice. And also we've seen an occurrence of internal choice in the queue, where when we dequeue, when the client sends the dequeue request, then the queue responds by indicating whether it's empty or not. And that's exactly the internal choice. So also note that for those of you who are familiar with polarities of connectives, we have the following. So external choice is negative, and internal choice is positive, has a positive polarity. And actually that's interesting. I mean, if you haven't heard about polarities, don't bother about it. I'm just providing this additional information. So in our session-typed interpretation, actually positive connectives are sending and negative connectives are receiving. And that will hold throughout. So you will see that. So let's look at the next two connectives. They dealt with what? Send and receive, exactly. So here lolly is channel input. So you can see again that's a negative connective. That's why I organized them in this way. And tensor is channel output. So sending a channel, that's a positive. And always, it's important that because we use this intuitionistic formulation, we always describe the type from the point of view of the providing process. So, so the polarity again is from the point of view of the providing process. And that's termination, process termination. Or what we said earlier, to kill a process, right? That kind of was fun at the time. And that's also positive. So the provider is going to close, and the client is going to wait for the provider to close. All right, so that's where we were at. What we haven't looked at is some judgmental rules. I'm not sure, do you remember any judgmental rules from the review session with Paul in linear logic? What I mean, judgmental rules, what I mean by this is rules that are not specific to a connective. So one such rule is cut, right? You've heard of cut, and you've also heard of identity, or I think Paul also called it axiom, or it's also reflexivity. I mean, there are different names for it. Okay, so what does cut do? So let's look at cut. And again, I'm going to use two different colors. So we first look at the logic rule. So with cut, we are given a context delta and delta prime. And now I need again to leave some space for the process term. And then we can prove a proposition C from it. Okay. So then, if given delta, we can prove an A, and given delta prime and an A, we can prove a C. So that's cut. So now let's look at it, or let's fill in the obvious part, right? We add the channel in order to now fill in the, so I'm going again to do the same game. We add process terms to it. So let's first fill in the channels. So here, to be consistent with what I did previously, we always used, in a case like this, the channel C. So then obviously here, we need another channel, right? So that's going to be X. And since we have here an A, so presumably that's also going to be offered along X. So what does the rule basically say? It says, well, if I can prove an A, then I can use it in order to prove another goal C. So as you can see that essentially we prove or create a new A, and then we can use it over here. So in some sense, we had a similar situation also with channel input and output, right? All of a sudden, we got a new channel. So, and that kind of motivates now to view this as spawning a new process. So in process terms, basically, we say, okay, I'm going to spawn along X a new process P, And after that, I continue as a Q. So that means this guy is the P that I just spawned. And then after I spawned it, I'm going to continue to, I'm basically going to proceed with executing Q. So that's parallel composition in the PyCalculus. Or we can also think of it as spawning a process. All right. So now let's think of the other rule, which is identity. That's really an easy one, right? It basically just says, okay, if I am given an A, I can use this in proving an A. That's identity. So let's annotate this with process terms. So again, we'll offer along an X. And obviously, we somehow have over here, along a channel Y, we already have get offered an A. So what are we doing? We're doing kind of a form of delegation, right? So we basically say, forward X to Y. So meaning that whatever our clients will get, they will actually get from Y. So now you might think, how are we going to implement a forward like this? And later on, we'll briefly look selectively at some of the dynamics in order, basically for our connectives. But just briefly, what do you think? How would we, if we were to implement a compiler for our language, how would we implement this behavior? Obviously, there are several possibilities, right? Well, do you have any suggestions? So the idea is, to get the idea across, the idea is that the client, so if I'm speaking now in terms from the point of view of this process, the current process that provides this service A along channel X. So this process will henceforth no longer provide the service, but instead the process that offers along Y will offer the service. It's a form of delegation, right? It's like when I'll say, okay, I'm not going to teach tomorrow, but instead Bob can teach for me. So that's the same thing. So how could we do that operationally? Well, yeah, it's a kind of substitution, but so essentially there are several options, right? We could, in a sense, you're right with substitution. What we could do is basically at the side of our client, so whoever is our client, we just plug in for the occurrences of X, we plug in the occurrences of Y, right? That's one option. Another, and then basically the process itself can terminate. It can cease to exist, right? We could kill that process, but before that, just make sure that we substitute appropriately. Alternatively, we could also continue to exist and basically just be a pure forwarding process, right? Whatever we get in here, we forward to this guy, and whatever we get from this guy, we forward to along channel X. So there are different options. Question?
So once process exists, so the data which is there on the process, will it get copied to the new process, or we are starting from the scratch?
No, very, very good question. So what happens, basically with the data. So in order to forward, the only thing that is required is that the two processes are of the same type. Okay, so exactly, so that's the only thing that matters. So in a sense, internal state is in this way not carried over. It's just, it's purely, what counts is that the type, the behavior that is described by the type is going to be, matches.
Why do we need this kind of thing?
Why do we need forwarding? Well, it'll become clear when we look at the queue implementation. So maybe hold off for a while. But it's very handy. It's also a very powerful construct. To be honest, when you do, for example, when we extended work to incorporate sharing, forwarding caused a lot of headaches. I mean, it's a powerful construct, and with power usually there comes a lot of responsibility, which is so described this. Well, I'm not going to say anything anymore.
So
No.
one last question. So isn't it similar to exiting the previous process and creating the new process of same type?
Yes, you can think of it. That's a kind of a version of it. Yes, you can think about this operationally in this way. Yeah. All right. So one thing I want to point out is now that we looked at cut and identity, I would briefly like to review basically lolly and tensor. So over here, I didn't write down tensor, but for tensor, it's basically the analogous thing. So what I want to point out for lolly is that basically what we did is, in order to send a channel, we spawned a new process and then sent that channel, right? Well, that's kind of a special, or that's kind of the. But you can imagine this. You can imagine also a special case of this, where we actually already have spawned earlier a new process, and now simply have a channel sticking around here. So our delta would basically consist of a channel that is of type, in which case this rule, this premise here becomes the identity, right? And then we simply send a channel. So basically we don't have, right now the rule is formulated such that we first spawn and then we send a new channel. But alternatively, we could already have spawned a process earlier somewhere, and then basically just take that channel and send it along our offering channel. And I'm just pointing it out. So the reason why I presented this rule initially is because it nicely corresponds with the intuitionistic linear logic rule, right? But for practical programming, we also want to be able to essentially just, send a channel that we have in our context. And still then the correspondence holds, because in that case the delta just becomes the channel, just one channel, and we have here identity. Okay? I just wanted to point that out. And the same holds true for tensor. Okay, so the reason why we looked at those two rules is because they're really fundamental. I pointed out that identity is very powerful. And another reason is that cut, it is also what gives rise to the computational flavor. Or cut is basically what allows us to give basically a computational meaning to this correspondence. Because in particular, it's cut reduction, which then gives rise to message exchange. I don't want to go into cut reduction. For those of you who are interested in this, can look it up. There, I can also point you to lecture notes. The idea is the following, that what happens, cut basically brings together a left rule with a right rule. So we have here a provider that meets with a client, and cut brings them together such that they basically can talk with each other, right? And cut reduction, what cut reduction does is it's a way of proving that your left and right rules are so-called in harmony. That it's a way for us to basically do a sanity check when we devise a logic. So cut reduction is one check basically we apply. And what cut reduction does, it pushes the cut at a type up to a smaller type, which means essentially in a computational way that we make sure that we can cut also at the continuations. All right, that's basically what I want to say. You can look up those things. I don't want to use more time on going into the details here, but just get the idea. So the idea is that cut really facilitates computation. That's what the Curry-Howard correspondence relies on. Okay, so we have now worked out the correspondence between the connectives of linear logic, intuitionistic linear logic, with basically our session-typed interpretation, right? And we've also seen that cut gives rise to computation. So now what is missing? So we are going to devise our programming language that uses linear session types, right? That's what we've done. We now have the typing rules. What's the other thing that we need to formalize our programming language? So we have the type system. What's the other thing we need? Right, we need the operational semantics. That's also what you wanted to say, right? Okay, so let's just look at it very quickly for a number of rules, because you already got the main ideas, right? You played with implementing message passing processes before. So let's look at some rules selectively. In terms of the operational semantics, I'm going to use a multi-set rewriting system, which, let's write that down. So that's how I'm going to express the operational semantics, which in short, it basically says that I can rewrite a system that is, I denote here with S, to a system I denote by T, where the system basically is described in terms of predicates that describe that system. And so we have a transition basically. So the key now for the multi-set rewriting system is that they work locally. So the entire system in our case is essentially composed of a set of predicates of this form. So let's put that here. Or let me write this differently. Let's call that C1, and then we have Cn. Okay, so the state of our configuration of processes is described by a set of predicates of this form. So proc C, P, which is very intuitive to read. So the first argument indicates the channel along which that process offers, and the second argument denotes the process term that the process is currently executing, right? So using those predicates, we can describe an entire configuration of processes. And now I use a configuration. Well, what is it in our case? It's a tree of processes, right? So we can describe our tree that we get at runtime with those predicates. And then the rewriting rules basically only indicate the predicates that are affected by the rewrite. And everything else remains unchanged. And of those of you who are familiar with separation logic, there is a similar idea that you only describe basically the footprint of something. You only describe what changes. So it's the same idea with multiset rewriting rules. Okay, that's the schema. Let's look at one rule and then you're good to go. So let's look at the rule for termination. So that's the rule for termination. So we'll have, so when I write down those rules now, one second, I'm always writing to the left the client and to the right the provider. The question, yeah?
Just to clarify, T is also like a state expression?
It is, yes.
Expression.
Right. Maybe I should use S prime instead. That would be maybe more helpful. Exactly. Mm-hmm. There's also, depending on your formalization, there might be some other predicates you use, but these are the main predicates we use, okay? All right, so what do we have? We do have a client process that is executing along some channel C, and it's waiting on a process that offers along a channel A, and after that, it executes Q. Okay, that's one process. That's our client process. Once again, this process offers along channel C, but right now it's trying to talk to the process that offers along channel A, and it's basically waiting for this guy to terminate. Then after that, once that interaction happens, this process is going to execute Q, which is its continuation. All right, so we do have also our provider that provides along A. What is this guy doing? Well, it's trying to close its channel. It's trying to terminate, which means it's going to execute close A. All right, and note, after the close, we don't have a continuation because we die. All right, so now we describe the rule. This transitions to, what does it transition to? Any guesses? I heard it, I think. Yeah, so it basically transitions for sure for the client, right? Client transitions to executing Q, offering it along C. What happens to this process over here? No longer there, right? What a stupid question of me to ask. So, and note, this is a local description. So that's the nice thing about multiset rewriting rules. We only capture in the rule what we touch, what we change. Everything else just remains the same. We only describe locally in the configuration what things change. All right, so we'll look at, maybe let's look okay, let's look at external choice. So we do have a client, right, that offers along some channel C. And now this client indicates its choice that it is offered by a process A. So along channel A, it is going to send a label, and I'm using here the subscript H to indicate the particular label that I'm choosing. And after that, I continue as a queue, executing queue, sorry. So we have over here, we have a process that has to offer along A, and this is executing the case statement. And now I'm actually switching to n-ary choice. Okay, that's why. So basically, then we have case A of. I said it. I forgot. So case A of. And then basically here we have a sequence of labels that we match onto process terms, and I'm using the bar notation to have a sequence of those things. Yeah, exactly, that's it. So what does this step do? After having indicated the choice, what does the client execute? The client? Queue, right? So process, the client process has indicated its choice, and now it happily continues with queue, right? But you're right. For the provider, it now has to execute the P that corresponds to the label L sub H. So it's going to execute P sub H.
Doesn't the client wait till the execution of all of PH finishes?
No, because we, no, that's not the semantics of the external choice. Because P can be a whole thing, it can be a sequence of several terms. It just waits, the two just synchronize. So the client indicates the choice, and then the provider executes it. I mean, look also at the rule here, you see? So after that, in the continuation, the client executes queue. Okay, question?
I just don't really have the semantics down here. Label sub H.
Yeah.
H is, what's H?
It's just a particular index. So I generalized here to n-ary labels.
Okay.
So we have a sequence of labels. So you can, the L arrow P bar, you can read as L, L1, arrow P1, L2, arrow P1, and so forth.
An arrow means?
Oh, it's just, I'm sorry, it's just syntax, like in functional programming, for example, when you do a case.
Oh, great.
Yeah,
Awesome.
yeah, I'm sorry, yeah, it's just syntax, just a process term syntax. Okay? Okay, so now, let's look at cut, where we spawn a new process. So, well, we start out with one process, right, that spawns a new process. So, this process offers along A, and it spawns a new process with term P along X, and it continues as a queue. Not as a queue, sorry, it continues executing queue. So, what does this step do? Well, surely we still have a process that offers along A, and it's going to execute Q, right? I left some space here because we'll see why. Well, but we spawned a new process, so we create another process, right? So there's going to be another guy. and that has to execute along some channel. What is it executing? P, right? It's executing P. Well, okay, what am I filling in here? So, well, I created a new process, so I also have to create a new channel along which that process offers. So let's do that. It's going to be channel B. So we have here the site condition that B is fresh. So we create a new fresh channel. And now what can we do over here? Well, actually, this is a binding occurrence of X. So in X will occur. Process over here, spawn the new process using using a new variable X, right? Now that we have spawned the new process and created a fresh channel, we plug in that channel for X in Q. Okay? Questions up to here?
Would that be forward of B to X?
Forward is a separate rule. We look at it next. Okay, shall I talk you through that rule again? Would that be helpful? Because I see some puzzled faces. Who's for me talking you through it again? Okay, so let's do it. All right. So we have a process that offers along channel A, and what does it do? The next thing it executes is spawning a new process that the body of the process is the process term P, and it spawns that along X, which is right now just a variable that stands for the new channel that will be created. When it has spawned that process, it will execute its continuation Q, and we can see that we have a binding occurrence, so X will occur in Q, right? Because we spawn another process for a purpose because we're going to use it in our continuation. All right, so that's our pre-state. Our post-state is now that we do the computation, which means we are spawning a new process. Okay, so that means the client still exists, right? So there's still the process that offers along A. Because it has stepped, the process is spawned, it is now going to execute Q, its continuation. All right? Because of the spawn, we create a new process. Well, this process will execute the process term that is given up here, which is P. You can think of it as the body of the process, right? When we write a process, basically. So that's the thing this guy is going to execute next. And because it was just created, we also have to create a new fresh channel along which that process offers. That's the channel B, which we create here fresh. Well, now, the client still thinks that it can contact the new spawned process along X, but X is just a variable. So at runtime, we substitute, like in a functional programming language, we substitute the actual thing for it. The only difference is that channels are, Bob Harper refers to in his book as assignables. But that's just a side remark. So we plug in the channel B, or actually a reference to the channel B for the variable X. All right, now we're good, right? Okay, so question over there.
Is that left arrow a binder?
Yes, yeah, so it's a binding occurrence. But here I just use the left arrow to indicate a spawn. I spawn something, but it binds the X in, so the X is bound in P. Okay? All right, so lastly, let's look into, I identity, so forward. Well, we have the following thing going on. We have a process that offers along A, and that process has in its context just one linear thing, which is Y. I want you to catch that. It's important that there's nothing else in the context than the Y, because otherwise we would violate linearity, right? We would, in particular, what would we violate if there were other things in here in delta? On what in particular? Weakening or contraction? Weakening, exactly. So now we have here a process that forwards A to B. Well, what does that step to? Well, now that depends how we decide to do that. One way is to do a global substitution, where we basically say every occurrence for A should now be an occurrence of B. So we basically plug in B for A. That's one option. We could also alternatively kind of keep this process alive and just have it forward whatever it receives on both ends. Okay, so now we've done enough formalism for now. So I'll turn this on and then I'll get to your question. Let's play with concurrency not. Okay, so what's the question?
Cut reduction. So shouldn't be the P also substitute X for B for the process P in the step. Since we allocate.
Yes, that's true. That's true. But as I wrote it, I basically I didn't, because internally P might use a different name. So it really depends. Once we have process definitions, we have to do this. But yeah, okay. All right, so let's do some coding. I think this thing needs a while to warm up. So let me then, in the meantime, so now we have to unfortunately switch syntax, because concurrency not uses a slightly different syntax. Because why? Concurrency not is extends. Let me see whether I can plug it in already, because don't want to miss the moment. Oh, it says no signal. No. Why? I'm okay. It's coming. Yeah, it is good. All right. So let's get it, because I know with those things sometimes they're kind of when they're ready, you have to be attentive immediately. Afterwards, they might go into some sleep mode or so. All right. So concurrency not is an extension of C not that adds basically session types to C not, and C not is a language that was developed for teaching purposes at CMU. It's a safe subset of C, and it supports also contracts, which means pre and post conditions and loop invariants. It comes with dynamic checking of those contracts. There's no static verification of the contracts. So for those of you who are familiar with, let's say, JML or Spec Sharp, it's something along those lines. But Spec Sharp comes with verification. And so having had that compiler basically already ready, session types were basically incorporated in it, which means we have to live with the C syntax. And you might find it helpful because I posted some material, and in there there's a PDF which is called, I think, Seal to Concurrency Not or something like that. And there's an overview table where you can see the different syntax. So let me briefly remind you or go through this together. Just very briefly. So we have this in the syntax I use in the course basically. So we have this, for example, for the external choice, I'm switching to n-ary choice. So basically, an external choice provides you a sequence of labels and types. Okay. So this actually, so now, how is choice encoding in concurrency not? Well, we use structs and then a special notation to indicate whether it's basically input or output. So in general, and that actually goes in line with the session type syntax we saw in the first lecture. So in general, bang stands for output or send. So some people use output for sending. So if you go into session type literature, you sometimes come across output instead of send. And then the question mark basically denotes input or receive. So that's basically it. So that means, for example, for tensor, so let's write that down. So for A tensor B, in concurrency not, we have, oh, and maybe I should also point this out. So if I have a channel C of type A tensor B, then that will be in concurrency not. It will be $C. So we always use dollar to note a variable of type of a channel type. And that will be of, and we use those angle brackets, bang A semicolon B. So we use angle brackets to denote session types. And then you can see, rather than an infix notation, we use a prefix notation. So it says send A and then continue with B. So that, and the same thing holds true, just the analog, the inverse thing for lolly. Then let's do termination. That would be in C naught, would be just the empty. So the brackets basically denote a sequence of things, right? So it's going to be the empty sequence. And then a little bit more involved is the external choice or choice in general. So here in C naught we have $C is of type, and now basically we use again the question mark. And then we use the choice, which basically corresponds to a struct in C, and the braces, open braces, and then we just have essentially here a sequence of types and labels. All right. So let's look at some examples. So now I have to type while I'm talking. So let's see how that goes. I had some practice already. I did a large undergrad class, 500 students, teaching them C naught. Well, I only taught half, but so once I didn't have my laptop my laptop crashed and I had to switch to a different one, and I didn't have my Swiss German keyboard, and that was a major challenge. So anyway, I thought I'll entertain you a little bit. All right, so what you have to type is you have to use some library. That's this, and that's basically so that you can do print statements. And when you code in a language like this, you want to be able to print stuff, right? Basically using it as a debugger. All right, so we are going to implement our queue. And let's first define our session type, okay? So, and I think we all remember what that is, right? It gives us, it's an external choice, providing the choice between an enqueue and a dequeue, and then we have a nested internal choice, and so forth. Well, okay, there's already a problem, right? I said we have an external choice, and nested within it, there's an internal choice. And structs in C cannot be nested, so, or in concurrent in C not, so we have to basically come up with two definitions. So let's do that first. So the font is big enough, right? Okay. So we have a type def, and now we say, okay, this is a session type, and I call it queue. And now let's fill in what the session type is about. Well, it's an external choice, so we use a question mark, right? Okay, let's do that. And then we have to use the keyword choice to indicate that's a choice. So, but internally that's like, you can think of it as a struct, okay? So, choice queue. So we do a type def. So henceforth, it's like with C structs, right? So we basically say this entire thing now we can henceforth refer to it as a queue, and meaning that's going to be an external choice. So far so good. And now I said that we have to kind of dissect the thing. So the inner internal choice, we have to make a separate type def with it. So let's do that. So we have type def. Again, let's do the session type. And now we call this QLM. Thank you. That's a laser pointer, I guess, right? Okay. Wow. All right. So I just call it Q element. And you will see later why it makes sense, because it's the internal choice where we indicate whether it's empty or not. But names are sometimes well chosen, sometimes less well chosen, and sometimes it's really difficult to come up with a good name. So anyway, so what's that going to be? It's an internal choice. So what am I going to use here? Bang, right? Okay, let's do that. Exclamation mark. So it's not the bang from linear logic. And it's again a QLM. All right, so we set up the type definitions. So let's now go and define them. So that's how we do it. We say choice, that's analogous to a struct, basically. So let's do first the first thing. So that's the queue. And we use the nice curly braces to do that. And now I'm going to indent that a little bit. Well, all right, we have two options, right? Two things we let the client choose between an enqueue and dequeue, right? Okay, now I have to switch on the fly because I have here insert and delete. So I'll be prone to make that error, but I'm going with now also enqueue. That's one label, and the other one is dequeue. Okay. So, and because we're in C, we basically have the type before the label. So now we have to indicate the type, which again comes, because it's a session type, it comes in those angle brackets. So what's the type of the enqueue? I mean, what comes after the enqueue? Well, we'll get, okay, so the client says enqueue, and then what do we expect as the queue? Yeah, we expect to receive something, right? So, okay, so here comes another thing. We don't have polymorphism in concurrency not. So we could use like, void pointers. That's one option, but I don't want to deal with pointers here. So let's just stick with integers.
Why is there no polymorphism?
There's no fundamental reason not to have it. Right, but it's a subset of C. So, one reason is that in that class, the students get introduced to a civilized way of programming C with pre and post conditions, and then later on we basically transition to full-blown C. So with the intention that they've learned how to program imperatively by thinking about the code using pre and post conditions, and then afterwards they jump into the big C. Okay, so all right, so we expect to receive an integer, and then we just continue to be a Q, right? And then with the DQ, well, what is now DQ, right? That's the internal choice. And that's the thing we define that's going to be the Q element. So that's going to be this. All right, so we have defined now the external choice. Now let's define, so if you don't mind, I think I'm not going to do a line break because otherwise you won't see everything anymore. So I'll just add that underneath here, right? So now that's going to be Q element, and again, so what's that going to be? Well, there's one label none, right? And there's another label which will be some. So what did we do at the time if it's none? We just terminated, right? So it's the empty sequence. That's what we are going to do. Then otherwise, what are we going to do? If there is an element, we can DQ it, so we send it, right? We are going to send an integer, and then we are a Q again, and actually now we're really, so notice this, we recurse back to Q rather than Q element. All right, so now we have our type definitions. So let's do next, we are going to implement our Q, which means now that we have to write process definitions. So C0 allows you to define process definition. So you write down the signature and then you provide the implementation. So that's going to be interesting, right? So now, unfortunately, I have to scroll a little bit, so you're losing some context. I can go a little bit smaller with the font. I'm not sure what you want. Okay, if I don't hear any objections, I'll just continue. Talk to me. All right, so here's now the thing. What kind of process are we going to implement? Well, we could do one process, right, that implements this Q. But note already, we basically, so imperatively, how would we do it, like in C or Java? Right? We would have a Q, and if the Q is empty, its next pointer is null. Okay. Well, and that's actually really like another kind of meta thing I want you, kind of takeaway message. Well, that's how we've been taught to program so far. And dealing with null pointers is really tricky, right? Because often we forget to make sure or to check whether they're null or not. And then we have, like, our code might be wrong. So how do we deal with it here? Well, notice already that at the level of the type definition, we have this distinction between the external and the internal choice. And in particular, the internal choice is a way for the process to communicate something about its state, right? The internal choice lets the provider indicate to the client whether it's empty or not. So we don't have any need for null pointers anymore, right? So then how about that? How about we implement two processes, one representing the queue when it's non-empty, and another one that is representing the queue when it's empty. So what will be the difference? So for the empty process, when it gets asked, or when it gets the request to dequeue something, it will just say, I'm none, right? And the full one will say, yeah, I'm some. I'm okay, go ahead. So, and for enqueuing, they're both kind of basically happily fulfill the request in the same way. Okay, so that's kind of a fundamental difference how we program, right? Because now we have, the types are expressive enough for us to do it, I'd say, properly. And allow me to be a bit judgmental here. Okay, so we are going to code two processes. One process is going to be, let me start with the empty process. Okay, so we call the process empty. Okay, that's just the name. And it actually doesn't take any arguments. And then as you can expect, what did I do? As you can expect, we have the curly braces. I'm not doing it the C style, I'm sorry, I kind of like this better. So, what kind of session is it going to offer? We have, let's scroll up. We have two session type definitions, queue and queue element.
Yeah.
Yes, okay. So now we have to indicate basically, so we say, it offers a session of type queue, and it offers that a long channel $q. So we use dollar to denote a channel. All right, so now let's go into there. So queue is at its outset. Oh, wait, I can actually split the screen. Let me do that. You know, Emacs, isn't it wonderful? Right, and then I pull this up a tiny little bit, and then I can pull this down a little bit, and then have I everything? Not quite. Well, okay, let me, I cannot do everything.
One window and leave another window.
Oh, you mean just the size? Oh, that's the shrinking work on that level? On buffer level? Ugh. Now I don't know what the shortcut is. Yeah, I know that's what I tried, but I must have screwed it up. But I can do this. No, it does everything. Okay, too bad. All right, I'm sorry about that. Well, what I could do is I can do here the Control 3, right? And then helps an awful lot. Okay, so I think that's on the, I think I don't have to have the, I'm not sure. It's no longer that helpful, I'm sorry. So let me just go back to, because you all have the protocol in mind, so let me just enlarge this. Okay, so now we are inside the body here. So it's an external choice, right? So we have to basically case analyze, which because we are in C, it's a switch. So we switch on our offering channel, and so let me move up a little bit. So now we have basically case. If it's an enqueue, then we do something, and otherwise, if it's a dequeue, then we do something else. So let's see what we do if in case it's an enqueue, right? Well, when it's an enqueue, we'll receive an integer along the offering channel. So we are going to say, okay, receive along queue an integer and store that into y. And then what should we do now? And actually now I have to briefly set up the other definition. So we said that we are going to have two process definitions, one representing the empty one and one representing a non-empty queue. So let's define that too. So we have here also a process that offers a long channel queue. I just use the same name, it doesn't matter here. And I call that element. So, and this process now takes an argument, actually 2 arguments. One is the local state, right? You asked that question in the first lecture, okay? So it captures what kind of element it holds. And then also because, remember, it's like a linked structure, so it has a reference to the next element in line, which is also going to be of queue type, and let's call that OR. Okay, so that's basically the signature for the other guy. So let's go up here. So now we have received that. So far we've been empty. Well, when we drew the picture, what did we do? When we get something and we were at the empty queue, well, we basically created a new empty one, which is the sentinel I referred to, and I saw that there were some questions on Slack about this, so you get the sentinel, you see it now in practice. So we have to create a new sentinel, and then basically what do? We recurse as an element. So let's do that. So we are going to create a new element, which is the empty one, okay? And now we do the following. We say, henceforth, we recurse as an element that has the y as its state that I just received, right? And its next thing is the e I just created. All right. So let's go to the DQ case. Well, if it's a DQ, then we are now required to tell the client whether we are empty or not, whether we are none or some. So what are we going to say? Well, we are empty, right? So we say none. So we send the label none along the offering channel. Okay. And then also in the linear setting, it makes sense because of linearity to close. So we are closing the offering channel, which we do in C not like this. All right. So now you can do. So what do? So actually, so I leave it up to you. I would like to say a few words before ending this lecture. That would be my preference, to say a few words about type safety, because in the self-study session you can play with this, because I indicated a directory with some test cases, so there are complete concurrency null programs which you can execute. Okay, there's also, because you can play with it and actually execute it. So if we were to continue, we would implement the element process, which is, I mean, once we've done that, you can figure out the other one. And then we also were to add a main function, which is basically a C main function where program execution starts. But you can figure that on your own, I'd suggest. So what I would like to do is I would like to talk about type safety a little bit. Does that sound like a good plan? Okay. Where is it? All right. So, because I heard that Jim encourages everyone to leave the room at noon sharp. So, I dislike that, but all right. So, let me see what okay, so type safety. in a message passing concurrent programming language as the one we devised right now. We are in the linear setting. And so what's the slogan for type safety? Which are the two theorems you have to prove? Yes, progress and preservation. Well, actually, I have to now say this. There's, what was it? I think students at CMU or so, they made a T-shirt. And on the T-shirt, they had Harper and Crary, progress and preservation for the US, or something like that. It's very funny. So anyway, if you didn't get it, then no worries. Okay, so it's progress and preservation. So we've already talked about preservation, right? Which we kind of phrase as session fidelity in this setting. And so what can you tell me now about preservation? Do we satisfy it in a linear setting? Who's for yes? Okay, so, all right, yes, we do, right? Because we saw with the linear restriction, we basically make sure that there's always exactly one client. So this guarantees that this single client will always align with the provider in terms of the expectations towards the session type, right? So there's no way that the two do not align because there's no one else interfering. All right, we've seen that preservation holds because we are in a linear setting. So that was our whole motivation, basically, why we set it up. So let me write down, and let's go away with that. So I just, because I somehow would like you to see how this theorem is stated. I don't go into details, but you know, if you want to read up in the literature, you've already seen it. So essentially what we do is we have to describe preservation for an entire configuration of processes. So when we looked at the dynamics, we saw that we can use those predicates, proc, right, in order to describe an entire configuration. So now I introduce omega, and that stands for either an empty configuration or basically a set of those proc predicates. Actually, I don't need the subscript 1 here. Okay. With an omega prime. Okay, so using now omega to denote this entire configuration that we have, that our program consists of, now we can state preservation as follows. Okay, preservation says, if we start out in a well-typed configuration, and now what is a well-typed configuration? This is basically the judgment I use. I'll explain that a little bit, just hang in there. So we have an omega, we have a configuration omega, and it offers channels in delta. This is again, these are linear channels. Now you are probably surprised, why does it offer like channels? I'll explain that in a minute. So if we have a well-typed configuration and this configuration takes a step from omega to omega prime, then, and now you can fill in the gap, right? Omega m is also well-typed. So we have this. Omega prime also offers the same linear channels. Okay, so let me explain what's the deal with this. So essentially, this is a deductive definition. It allows us to decompose our tree that we get. So the omega really is a tree, right? That's what we found out so far. So we essentially have here the root node that spawns all other processes what's that going to be? That's going to be our main process in the concurrency not program, right? That's the only one, that's the root, that's the only one that hasn't a client. So, and then basically we have other nodes that are again, have other subtrees. Okay, that's our omega, that's our configuration. So that means at the top level, this is going to offer, so here, let me use another color. At the top level here, we are going to offer just a session of type 1. Because the main process just, once all the computation is done, it's going to close, we exit. All right, that's at the top level. We just offer along the root channel basically, we offer the session of type 1, which will eventually close when the program terminates. Okay, so, but in the proof of preservation, we will use induction, or in general basically also, in particular actually in the proof of progress, we induct over the configuration. So that's why it's helpful to have an inductive definition here. So we can actually basically go level by level and basically take off this root node. And then what will be in the delta? So for this configuration here, let's call it omega double prime, not to confuse with this one over here. Well, this one will actually offer, what will it offer? It offers all the sessions offered by those nodes here, right? So let's do this maybe x1, and this is offering along xn. So we have here x1 of, let's call it b1, xn, bn. Okay, so that's just a very brief explanation of how this judgment comes about. If you want to know more, I'm happy to do that, but offline. All right, so can I talk about progress? Or shall I move it to the, I need like 5 minutes, is that okay? Everyone okay with it? Good, okay. Because that's actually really cool, because I can tell you why progress works in a picture. And I'm very happy about this. And I only found that out recently in my own work, once I tried to kind of deal with deadlock. So, all right. So, let me first explain what the difficulties are with progress in general. So when we have this tree, the configuration, right? So our program is basically a tree of processes, right? We're all good with that. So I guess if you took something along, I guess that's certainly it. All right, so that's our program. It consists of a number of processes. So what we've seen so far is that there are left rule and right rules, right? And what do they mean? They basically mean that the right rule is willing to talk along its offering channel, right? And the left rule is actually right now, when we're in a left rule, the process is not talking along its offering channel, but it's wanting to talk to some of its of the processes that it uses, right? So let me make this explicit again. So I'm a process. I offer along my offering channel. So I'm talking to one person in the audience because I'm linear, right? So I'm talking to her. I'm willing to talk to you. But after I talk to you, I might want to talk to any of the guys I'm actually using. So I might actually turn my back to you and I talk over there. So what if you actually still want to talk to me? Well, you have to wait, right? So that's message passing concurrency, right? So essentially when the left and the right rule meets, those denote the synchronization points. Those denote the times when they both are ready to talk to each other. So what does that mean in terms of the tree? Well, it can be that one is not ready for the other. So that means if we were to depict this in this graph, it can be that one is waiting for the other, and I'm going to express this with an arrow, where the arrow points to the guy I'm waiting for. So maybe the root is right now synchronizing with this node, so that means this guy is waiting, right? Well, because this guy is waiting for that guy, this guy here might also be waiting. So we get this, right? Oh, well, it could also be that that guy waits for that guy also. So you see that in general, if it weren't a tree, we could be waiting for each other. I mean, I could be waiting for myself transitively. So we could have a form of deadlock or a circularity. It really depends on what kind of notion for deadlock you mean. So that's a danger for progress. And you can see now that we use a tree, there's no way for us to create a cycle using those blue arrows. That's why globally, there will always be one process able to step, because we cannot have a cycle with those blue arrows. And why can't we have a cycle? Because the blue arrows only go along those edges, right? And the edges form a tree. All right. That's what I want to say.
With the lolly, we can send channels to other processes, right? Can that be used to follow
Oh, very good questions. Yes, lolly and tensor, they complicate things, right? We can't, what does it mean? Yes, very good question. Lolly and tensor, what do they mean? That we change the tree dynamically. However, it's still going to be a tree. So we're safe. But once we talk about sharing tomorrow, we don't get that anymore. All right, so that's for today, and I thank you for your patience and giving me a little bit more time. So see you tomorrow.